is a camera that can take pictures and videos of sound. But how does that work, and what does this have to do with it? In this video, I'm going to run through how this can take a picture of a sound wave. Since I put out the video on my senior design project, which was an acoustic camera, almost 6 years ago now, I've been wanting to do another video on this, and conveniently enough, a few months ago, a company that makes acoustic cameras, Fourier, reached out and offered to send me one of their new models, their TD2, if I was interested, and I figured that's as good a reason as any to make another video on this. This won't be an ad or an in-depth review for this model, more of an explanation of how the tech works in general, and particularly, why is it that every camera has this weird spiral swirly pattern on the front of it? So this is the unit they sent me. It's called the TD2, and as far as I'm aware, it's one of the first consumer-level acoustic cameras on the market. Nice and compact, and seems to work really well. I've been happy with the performance of it during some basic testing. Also found probably the killer feature. There's constantly like 1 or 2 crickets right outside my bedroom window.
There you are.
An acoustic camera takes pictures and videos of sound in much the way that a normal camera takes pictures of light, or a thermal camera takes pictures of heat. It shows you where the sounds are coming from. So, like the cricket there, you can find the source of noises accurately, whether it's something silly like a cricket, or more industrial uses like air leaks, machinery vibrations, or even something like tracking down a winding inductor or in a switching converter, or piezo effect noise from a capacitor. An acoustic camera really only consists of 2 parts, at the most basic. There's an array of microphones on the front that pick up the sounds we're looking for, and some kind of data recording or processing that takes information from them and converts that into an image. For this camera, there's 64 microphones, placed in this sort of spiral pattern on the front, and an FPGA and display built in, so it does all the imaging in real time. This brings up a bit of a question. How do we turn the data from a bunch of microphones into an image? This is a type of inverse problem, a set of problems not unlike the P versus NP type, if you're familiar, effectively in that it's very easy and straightforward to, given an image, figure out what each microphone in the array would pick up. But it's much more difficult to go the other way, to take the microphone data and convert it into a good image. What we're dealing with is taking a bunch of time-aligned sound recordings from each microphone and trying to use the tiny differences in timing to draw a picture of what's going on. Part of this difficulty is due to the sampling. We're converting an infinitely complex acoustic soundscape into a finite amount of digital data through these microphones. We're only measuring a relatively tiny amount of data, so we're losing a lot of information. And crucially, we're not even sampling the image itself. We're taking measurements of some other information, what sound is being seen at a number of different points in space, and then trying to convert that back into an image. There's really a couple of ways to think about this process. At the very highest level, you could think of it almost like a text description of an image. The sound itself being recorded isn't like that, but the general process is the same. We're perceiving the soundscape, extracting some information from it, recording only that simplified information, then trying to recreate it from that limited information. But that recreation will always be imperfect. Like, given a written description of some picture, you could draw a very detailed image, but there are an infinite number of possible images that would fit that description, and no way to tell which is closer to the original, given only the text description. The more detail you can put into that description, or the more data we can get from the microphones, the closer you'll get to the original, though it will never be perfect. This is similar to the mathematical concept of uniqueness of a solution, if you're familiar with that. One of the ways to think about how to do this more rigorously, or mathematically, is to simplify the problem as far as possible, and think about what happens for a single pulse of sound from a single source and with only a couple of microphones. So we've got a setup like this with some microphones in a line and something making noise over here, and it shoots out sort of like a single wave. Very hand wavy and abstract from now, but we'll get there. And that sound travels out and hits one microphone, then the next, then the next, then the next, then the next, and so on. We can represent that visually like this, with time going this way, and this dot for when the microphone hears the sound. And this graph, this data, is all that the sound camera itself can see. It just gets this microphone data without knowing what's going on out there, like that text description from a second ago. And we want to figure out from this where the sound is coming from. We'll do another example or two as well. If the sound is coming from straight in front, then the sound hits all these microphones at the same time and the graph looks like this. If it's coming from down here, then it hits this microphone first and then up, and so the graph looks like this. You might be able to see where this is going. If we just draw a line between all of these different points, and then draw another line at a right angle to that line, boom, that points to the direction the sound is coming from. This seems overly simplistic, but if you do the math to make this rigorous, this is exactly the equations we actually use for beamforming. This works in 2 dimensions too. Just instead of a line between these points, we're talking about a plane slicing through a 3-dimensional graph. So you could think of the data as sort of streaming out behind each of these microphones in the array. Same way it is here, but just for every microphone in this 2D array. And so we end up with a 3D set of data, plane slices through that, and then we're having a point at a right angle to that plane. The way this goes from a single direction for a single source to a full image is pretty simple too. You could think of it as sort of a hypothesis, test, and result for each pixel in the image. So we scan through pixel by pixel and hypothesize that there's a strong sound source coming from that direction. Then we draw the line that would represent that and look for sounds on that line. If there's not really anything that lines up well, like you see here, then the data doesn't really support that there's sound coming from that direction. And so this gets a low number, off pixel, a dark pixel. If there's a lot of points on that line, however, then the data does support that there's a sound coming from this direction. So that pixel gets a high number, or it's bright. And so we scan through for every single pixel in the image, do this process, and then light up the pixels that are sort of where the data supports that there's a sound coming from that direction. Do this for the whole image, and you get a map of how certain you are that there's a sound coming from that direction, and that map is the image. Moving this to 3D, I think, makes it a little bit more intuitive. In this render, the white dots are the microphone signals. The plane intersecting with them is our test line. The green line at a right angle to that plane is what points at the pixel that we're testing, and the blue squares are the actual image pixels. For the data being shown here, we should only see a single pixel lit up in the final image. To make that image, we sweep the green line to point at all the different pixels, check if the plane lines up with our data points, and if so, we light up that pixel. But we haven't really rigorously defined what it means for these data points to line up with the plane. Also, we haven't addressed the fact that we're looking at continuous sounds, not just an instantaneous spike. We kind of solve for both of these together. To start, we can switch from thinking about a point to thinking about a wave. We'll start with something like this and go to a continuous wave in a second. If we record some of these waves from the mics, so microphone array over here, and as the sound hits it, we make these graphs for a source coming from up here. The data for that will look like this. The end result that we want here is some mathematical operation on that line from a second ago that gives low numbers for lines in every other direction, but gives a high number for a line in this direction. The first thing that we need to do is transform the data. So the next operation is simpler. We'll sort of pin the data based on a vertical line like this, and then shift this to point at the pixel that we want to render. So if we want to render a pixel up here, we shift it like this. If we want to render a pixel down here, we shift it like this. And to render a pixel directly in front, we don't have to do any shifting at all because this line's already vertical. This basically offsets the data based on the expected time of arrival of the signal. So if we expect that the source is up here, then we would expect that the sound would get here first and then here and then here. So we shift it to line all of those up vertically. So we shift our data and then sort of unpin it and then look and notice that all of these are on a single vertical line. And this is true if we had our source down here. We would shift it these would be offset the other way, we'd shift it the other way, and then it would still be on a vertical line when we're pointing at our source. Also note that we're not looking at these graphs while we're doing this shifting just yet. We're just shifting it based on the direction that we want to look. So if we want to look down here, we shift this way. If we want to look up here, we shift all the data this way, regardless of what's in these graphs. Then we move on to the next step where we start looking at that. So once we've done that offsetting, we have data that looks like this. For a bright pixel, notice that all the waves are aligned vertically now. Bright pixel being because our source is right there. And for a dark pixel, our sources are not aligned vertically, they're separated out. So now we just need a mathematical operation that represents that hypothesis test thing from a second ago. So we get a big number for this and a small number for this. There are several different ways to do this at a lower level, but they all basically depend on that adding these waves together vertically at each point gives us a new wave, and the height of that wave corresponds to how well aligned these peaks are. So for a well-aligned graph, we get a single big spike, and for a poorly aligned graph, we get a sequence of smaller waves. And note that the peak of this is a lot shorter. It's 1 versus, it only adds up to 1 versus adding up to 3 if these are each a height of 1. This process also works for a continuous wave. We'll cut down to just 2, but it works the same with more. When they are aligned with each other and we add them up, then we get a bigger wave. When they're slightly misaligned, we get a slightly smaller wave. And when they're completely misaligned with each other, so the top of this lines up at the bottom of this, then they basically cancel each other out. We get nothing or almost nothing. Any sound is made up of a series of different waves like this at different frequencies, a spectrum. So this process works exactly the same for any possible sound we could be looking at. These waves just get wider or narrower. This does get us into some design trade-offs though. I'll come back to this later. But for now, just remember that this works for small offsets, but past the point where they cancel out, the sum of these two waves starts to grow again. So if they're a little bit past here, we go back to a medium amplitude wave. And if we get to the point where we've moved over an entire wave cycle here, we're back to the peaks lining up. So we go all the way back up to a full scale output. This will cause some problems, but we'll ignore those for the moment. And this is the core of it. There's a lot more that you can do, a lot of mathematical programming and trickery to make this more efficient, and a few significant changes that can be made to the whole process. But basically, this is the entire process from the data coming in from the microphones to an image on screen. Another completely different way to think about this whole imaging process is a bit like any other camera, as in like a normal light camera. Now, in a normal camera, the light comes from the world in front of you and hits the lens, and at some point behind it, what you see in front is recreated or projected. If we put an array of light sensors at that point, an image sensor, we can sense the light there and we'll get a recreation of the original image. The basic idea is that for any given ray of light hitting the lens, it has three parameters: its direction, its position that it's hitting the lens, and intensity or brightness. A normal camera sensor can measure only intensity and position. It measures the light level at a few million different positions, the pixels, and importantly, it doesn't care the direction that the light arrives from. If it hits a certain pixel on the sensor, it's recorded. So in a camera, we've got all these rays of light hitting the lens, and the lens redirects them in such a way that at some point behind the lens, we call this the focal plane, their position depends only on the direction they hit the lens coming from, rather than where they landed on the surface. So you can see here, like with these red lines, all the red lines coming from the same direction all end up at this point in space, even though they started at different locations. Same for the blue ones. They're coming from a different direction and they end up in a different place. So the lens is effectively measuring the direction that these rays of light hit it, if we just measure the position that the light ends up at. This is an important concept. The direction the light, or later sound, is coming from, not where it hits the lens, is what matters. And in fact, because of the way light works, while we can think of it as a thin ray, it is technically a wave hitting the whole lens at once. So it's more useful in this context to think of it as a wavefront. So the wave comes out from some point in the image, travels a distance to the lens. Notice that the line spreads out until it's effectively a straight line, and then gets converged back to a single point after passing through. This line is also called the wavefront. Much like if you looked at a wave in the ocean, it forms a line perpendicular to the direction it's moving. And notice that our light wavefront is perpendicular to the rays that we drew a second ago. In fact, it's always at a right angle to these lines by definition. Notice also how for a light coming from below, as it hits the lens, the wavefront sort of rolls up from the bottom of the top. It hits the bottom first and then over time hits higher up on the lens. So another way to think about this lens is that it's sort of measuring the way this wavefront moves across it and then directing it to a different point based on the way that it rolls. So if it rolls from the bottom up, it'll direct it up here. If it hits from the front all at once, it'll direct it in the middle. And if it rolls from the top down, that means the wave is coming from this way, so it directs it to a point down here. So if we just measure where the wave ends up, then we know where the source was. Then we can reconstruct an image by just measuring a whole bunch of different points, and then we know the intensity of light coming from a whole bunch of different directions. Well, between all these things, we can see that the lens itself isn't doing anything magical. It's converting information from one form to another. But if we can just record all of that information to begin with, then we don't need the lens itself anymore. We can do the same math on a computer and end up with an image all the same. So if we imagine a new kind of sensor that can record when the light is hitting it, not like a normal camera sensor that just detects how much, but one that records all the wavefront information, then we can recreate this effect on a computer. So we put our sensor here, where the lens would be, record all this wavefront information as it passes where the lens was. At this point, we've effectively captured all the same information that the lens did, how this wave is hitting it, just in a different form, digitally. Using that information to basically do a simulation of the lens system and image sensor within the computer results in an image all the same. Now, really, we don't actually need to run like a ray tracing rendering simulation of the light paths. We can simplify this to some basic trigonometry, which makes it computationally tractable to run quickly and on an embedded machine. And the sound camera does exactly this, just with sounds instead of light, because they're both waves. The math works out to be the same either way, just accounting for the speed difference. In fact, I got into sound cameras in general, after working on radars and antennas. I wanted to mess around with phased arrays and actually pulse compression for 3D imaging, based on some work I'd done as an intern. But the radio frequency stuff is massively more expensive and complicated, especially for something like this. With acoustics, though, I was able to get into this for only a couple of $100. So because we're using the microphones to gather data about the wavefront, and that data turns into the image, and the amount of data that we have doesn't change, the fewer microphones we have, the less data can be contained in the image. For a light camera, capturing less data means a lower resolution image. All the pixels are still the right color, there's just fewer pixels to work with. For this, because we're turning more abstract data into an image, we don't have a resolution per se. We can do the math to make an image at any resolution we want, but the amount of information in the image is limited. This turns out to give us a practical limit to how certain we can be about the source of a sound. There's two basic ways we can be uncertain about this. One is accuracy of exactly where the sound is coming from. Like it might be coming from right here, or it might be coming from like 1 degree to the left, and we can't tell the difference. The image is blurry. The other way we might not know is if it's coming from over here or from over here, but we know it's not coming from anywhere in between. There's effectively multiple copies of the image, directly multiplying our uncertainty. In an image, this shows up as sort of the size of the blob coming from a point source, or multiple blobs from a single source, respectively. The way this emerges from the math is related to how we added up the waves a minute ago. Remember this? Good times. So when we're making an image, we start by measuring the amplitude of the sum of these waves, shift them a bit to move where we're pointing, and then do it again, and keep that up until we've got a complete image. When they shift past this minimum, though, the signal keeps getting bigger until one wave over, it's all the way back at full strength. Now, if these are close enough together relative to the wavelength, then we might never move it so far that this causes a problem, as long as they don't get past this 0 here. However, this also means that the bright spot from our source covers the entire image. It only gets to 0 near the edges, so the image is a single big blurry spot, which isn't very useful. If we space out the microphones a bit, though, we measure right in front of them, we get full strength, we move them over just a little bit, a few pixels, and we're down to maybe 1. Move them over a tiny bit more, and we're all the way down to 0. So the size of the spot in the image has shrank. It's a sharper image. It's less blurry. This is significant. This tells us that the size of the array, relative to the wavelength, is what sets how sharp or blurry the image is. The problem we start to run into is that now if we go over even a little bit farther in the image, these add up to 2 again. And in fact, we get a whole line of these false spots every time these waves line up with each other. So we get a whole bunch of points in our image that shouldn't be there. And this gets even worse if we put the microphones farther apart. We can fix this, get the best of both worlds, by just throwing another microphone right here, though. Now, even though these two are lined up, this one isn't, and in fact counteracts one of these, so the spot here isn't as bright. The problem is this means adding another microphone. Ultimately, this is why sound cameras have so many microphones in them. It's a trade-off between adding more microphones, which means more cost for the parts and more powerful processing, against the sharpness of the image and avoiding these weird artifacts. It's sort of a pick-two thing. A small array with a few microphones won't have artifacts, but will be blurry. A big array with few microphones won't be blurry, but will have tons of fake spots in the image. And a big array with lots of microphones is expensive and complex to make, and physically unwieldy, but will make a sharper picture with no artifacts. And once you go to a 2D array, the arrangement of these and trade-offs between arrangements gets significantly more complicated. From here, we'll ditch the simple waveforms and go to simulations. These graphs show the microphone positions on the right Each of those points represents a microphone, and the resulting image for a sound coming from directly in front of the array on the left. You can see that with the rectangular grid, the spots are this sort of rounded rectangle, and the false images also appear on a grid. That's not a coincidence. The shape of the microphone array directly affects the shape of the resulting artifacts in the image. It's related to the 2D Fourier transform of the microphone positions. If you understand how those work, this should be pretty intuitive. If you're not, at its most basic, a Fourier transform is a sort of way of extracting patterns from raw data. So because of that, any regular patterns in the layout of the array will produce significant artifacts in the image. So we want an array without any simple repeating patterns, especially not on a grid. Also, for an array that is far from a circle, the patterns will take on sort of the reverse of that shape. So a very short, wide array will make a very tall, skinny spot. One way to think about this is as a measure of uncertainty. We're sort of collecting more information about the horizontal position because we've got our microphones more spread out in that direction. So we're more certain about the position of the source horizontally. So our spot is closer to a single point in the horizontal direction. Vertically, it's the opposite. We don't have as much information, so we're relatively uncertain vertically. So, since for general imaging there's not much of a distinction between horizontal and vertical, the array should be roughly circular overall, so we get a simple circular spot in the final image. Within that circle, we generally want to avoid any repeating structures, grids, lines, that sort of thing, as those will show up in some capacity in the final image. There's many different ways we could arrange these, including randomly, and they all work, but generally this sort of spiral ends up giving the best looking image. And if you look at just about any manufacturer, even up to the high-end flukes, they actually use exactly the same kind of spiral, just with some different parameters. You could do a really deep derivation to work out the perfect formula, but in practice, tiny tweaks don't really optimize this all that far. You'll also notice that not every spot in this spiral actually has a microphone. It can be a little counterintuitive that this still works, but basically, since we're sampling the wavefront, as long as we capture enough information to get a pretty good idea of what that wavefront is doing, our image should still be mostly accurate. Now, this does introduce some weird, random-looking artifacts, but that doesn't compromise the actual image quality too much. The main effect is signal-to-noise ratio. We can never exceed a ratio of the number of microphones we have, possibly -1. So having fewer microphones, 64 in this case, means that the best possible contrast we can have in an image is 64:1. Exactly which microphones are populated again could probably be mathematically derived, but practically it's better to do a combination of simulation and real-world testing. And when I talked with the engineer at Fotric, he said that's exactly how they did it here. I don't have a great intuitive analogy for how the arrangement of the array maps to the resulting image distortion, but I do have a script that can show it, so I'll just let a few of these run. given a point spread function, we can also simulate how a picture taken with that array would look. Hopefully with those, it's apparent why pretty much every commercial acoustic camera uses basically this arrangement. It's a good balance of artifacts and spot size, and spreads out most of those artifacts into a big dark ring, so it doesn't cause strong false points or distort the spot shape significantly. And that is basically how these things work under the hood, at least mathematically and in terms of signal processing, and why they're built the way they are. If you want to get one of these cameras, there's a link to Fotric's website in the description, and it's worked pretty well, and is one of the cheaper devices on the market. Thanks for watching. And yes, the next multimeter update is coming, eventually.